Hello my dear students, welcome to Impulse Batch. A very good morning to all of you.
Hello my dear students, welcome to Impulse Batch. A very good morning to all of you.
My dear students, please share the session, like the session. Like the session all of you so that I can get your attendance. Raviteja, Vamsi, share the session and like the session so that I can get your attendance, my dear students. Okay, as today is the first class in our Creatrix channel, I'll give a small preparation strategy how we are going to deal with our signals and systems. I mean, it will be of a very short duration. See, this subject called signals and systems is there common for ECE students, electrical students and IN students, right? Now for GATE 2002, how we are going to prepare or what is our strategy? Before going to see the strategy, let me introduce myself. I'm Swamy. I did my MTech in Systems and Signal Processing from J&T College of Engineering, Hyderabad, and passed out in the year 2007. And since 2009, I was into this GATE coaching field, teaching my favorite subjects, signals and systems and communication throughout the country. I have 12 plus years of teaching experience and now I am associated with Unacademy. And if you want to purchase any course on Unacademy, you can use my code KVS Live to get flat 10% discount on any course. First of all, we'll see what are the available courses in Unacademy for GATE. As far as GATE is concerned, we are having two types of courses here. First one is Plus subscription and the second one is Iconic subscription. So in Plus subscription, the student is exposed to live classes, structured schedule is given, test series, many test series are there, rank improvement batches are there, unlimited practice will be there. And apart from this Plus subscription, we have one more type of subscription known as Iconic subscription, in which the student will be under the supervision of a experienced educator known as mentor. So here a personal coach is given to the students, a detailed study planner is given, experts guidelines are given to the students, and we have mains, ESE mains questions and answers also in Iconic subscription. Now coming to the fee structure. So what is the fee structure if you are going for Plus subscription or Iconic subscription? If a student is planning for GATE or ESE, in Plus subscription for 12 months, that is for 1 year, it costs around 27,225 rupees, and again you can use my code KVS Live to get flat 10% discount. Means around in 25,000 you are going to get the course. And in this GATE and ESE only, if a student is planning for 18 months, that is one end of year, it costs around 34,650 rupees only, and again you can use my code KVS Live to get flat 10% discount. And in this GATE and ESE for 24 months, that is 2 years course, which is ideal for second year students. Second year students, this plan is very ideal because 24 months, if the student start preparing in second year, he will have more advantage. So it costs around 39,600 rupees only, and again you can use my code KVS Live to get flat 10% discount. And this one, this GATE and ESE, if a student is planning for 12 months, in Iconic subscription, apart from Plus we have one more subscription, that is Iconic subscription for 12 months, that is 1 year, it costs around 45,225 rupees, and again you are going to, if you are going to use my code KVS Live, you are going to get flat 10% discount. And in Iconic subscription, if a student is planning for GATE or ESE preparation and for 24 months, that is 2 year course, it costs around 66,600, and if you are going to use my code KVS Live, you are going to get flat 10% discount. Okay, Adarsh Kumar, good morning. Chinna, please reply me in chat WhatsApp. Yes, today you will get the reply. Okay, Chinna, good morning. Ramana Kumar, good morning. Sonali Suman, good morning. Sachin सर आप कंप्लीट कराओगे सिग्नल से सिस्टम पूरा कंप्लीट हो जाएगा. गुड मॉर्निंग. ओके, नंद कुमारन गुड मॉर्निंग. वंशी गुड मॉर्निंग. रवितेजा. राइट. So this is about the fee structure in plus subscription or iconic subscription. Now coming to the preparation strategy, what we are going to discuss. So we are going to divide our signals and systems topic into various units. In the first unit is basics of signals and system. I'll briefly give, I'll try to conclude this preparation strategy in a short amount of time. So in the first unit, anyway, I'm going to share this PDF in your Telegram channel, so you can see what all the topics we are going to cover. Okay, good morning Harish Kumar. So first of all, we'll see the definition of a signal, concepts of an independent variable, continuous and discrete time signals, transformations of the independent variable, basic signals. Basic signals means what are the step signals, impulse signals, signum, RAM signals, their properties, how to draw, how to add, how to subtract, how to multiply, and classification of signals. So what are even and odd signals, periodic and aperiodic, energy and power signals, causal, anti-causal and non-causal signals. And let me tell you that for the completion of first unit itself, it takes around 15 days. 15 days duration we are going to take, because we are going to discuss every basic in detail. And one more thing is, my dear students, remember that if you are perfect with the first unit, that is basics of signals and systems, the rest of the units will become very easy for you, because all the basics are lying in the first unit only, or all the hidden concepts are lying in the first unit only. So don't miss the first unit. Means for the first 15 days you must be very punctual to the class. If you are missing something, means you will face difficulty in understanding the next class, right? So you must be very punctual. So the next one is the systems. So I'll introduce the concept of systems, and we'll discuss the properties of linearity, time invariance, causality, static and dynamic properties, stability and invertibility, and non-invertible and non-invertible systems. After that, I'm going to start linear time invariant systems, in which we'll see how to represent any continuous time or discrete time signal in terms of impulses, convolution sum and convolution integral. Many problems on convolution sum and convolution integral we are going to do. Properties of convolution, like commutative property, associative property, distributive property, area property, we are going to discuss. After that, we are going to discuss the properties of LTI systems, right? Like causality, stability, how to determine any, or how to judge or how to classify any system as causal or stable based on the impulse response concepts we are going to discuss here. And what is step response, and we'll see the concept of unit doublet. This is about the second unit. Coming to the third unit, how you are going to find the frequency domain representation of periodic signals, that is Fourier series. So trigonometric Fourier series, calculation of Fourier series coefficients. So using symmetry, how you are going to solve the problems, how to draw the magnitude and phase spectrum. How many lectures are required for SS? We cannot say like this that these many lectures, because it depends on the topic. Rupal, minimum 60, take it for granted, minimum 2 months course you are going to have. Minimum I said, maximum I don't know, right? So after that, we'll switch to exponential Fourier series. We'll see relationship between trigonometric and exponential Fourier series, and we have to discuss various properties of exponential Fourier series with examples and previous gate questions. And every time a topic is completed, we are going to discuss all the previous gate questions and LTI systems using periodic inputs and discrete time Fourier series. After that, we'll go to continuous time Fourier transform. So what is analysis equation? First of all, we'll see how this continuous time Fourier transform came from continuous Fourier series. What are the convergence conditions? How to calculate the Fourier transform of basic signals like rectangular pulse, impulse, okay, exponential signal, we'll see. After that, we have to discuss the various properties of continuous time Fourier transform. This properties itself will take around 7 days time. 7 days time minimum for properties only, because we have to discuss the property and we have to solve the problems on each and every property, right? So this is about the continuous time Fourier transform. And after that I'm going to discuss the applications of continuous time Fourier transform, like distortionless transmission, in which we'll discuss what is group delay, phase delay, and what are the conditions for distortionless transmission, what are the conditions on magnitude response, phase response. And after that I'll introduce the concept of Hilbert transform, how Hilbert transform is different from other transforms, and how we are going to use Hilbert transform in communication. And after that we'll see the correlation, how to measure the similarity between two signals, what is autocorrelation, what is power spectral density concepts, and all we'll discuss here. And we'll see what is pre-envelope, complex envelope, and how to find out the continuous time Fourier transform of periodic signals. This is very important topic, right? Various examples are also taken on each and every topic, my dear students. Would it be full course, sir? Yes, it will be full course. And after this I'm going to take the next unit, that is nothing but sampling. So here we'll discuss how to introduction to impulse train sampling, how we are going to sample a signal, and how to find out the Nyquist rate and Nyquist interval calculations, and many problems, previous gate questions we are going to discuss, and transmission of a sample signal through a low pass filter or any kind of systems. This is an important topic. And after this we'll see the practical approaches of sampling, like natural sampling and flat top sampling. And in flat top sampling, what is the concept of aperture effect and how to avoid that aperture effect, and all this we are going to discuss. And we are going to have band pass sampling after this. This is about sampling, and this is what I am going to brief you in a nutshell. Anyway, each and every topic is going to be discussed in detail, that you only can observe. After that I'll go to discrete time Fourier transform. So analysis and synthesis equations, convergence conditions, DTFT. Discrete time Fourier transform is, in short, we can call it as DTFT. Basic signals and properties. See, every transform will have properties, and we are going to discuss all the properties, whatever may be that, in detail. And after that, determination of filter from difference equation, because sometimes they'll ask this question, very important, how to determine the type of filter, whether it is low pass filter, high pass filter, or band pass filter, from difference equation or transfer function is given, how to find out. Okay, so more emphasis is given to the fifth one. After this I'm going to take up tell me daily timings of classes, sir. Morning 7:30 sharp. So previous questions of ECR EE, everything is dealt. Aditya, do one thing, you come to the class for what I'm saying, 10 to 15 days, you only will observe whether we are going to discuss the previous questions and all the concepts or not. Aditya, daily timings are 7:30 sharp, morning 7:30 AM. And after that we are going to have the Laplace transform, and if we have Fourier transform, what is the need for Laplace transform, we'll discuss, and analysis and synthesis equation, and what is the concept of ROC, because in Laplace transform we'll get something known as region of convergence. Laplace transform of basic signals will calculate, and properties of Laplace transform, and unilateral Laplace transform, and how this unilateral Laplace transform is used in solving the differential equations we'll discuss, and analysis of continuous time LTI systems, like causality and stability using Laplace transform. The sixth topic is very important, Laplace transform switched periodic signals. Okay, and after this I'm going to introduce Z transform. So, and in this Z transform, analysis equations and the synthesis equations, means how analysis and synthesis equation is how we are going to find out the Z transform and inverse Z transform. And we'll see here the relationship between Z transform and discrete time Fourier transform. Z transform of basic signals we'll discuss, and properties common for every transform. Unilateral Z transform we'll discuss, analysis of discrete time LTI system using Z transform, causality and stability. These are very important topics. Many problems we are going to solve. Do we need to have prerequisites for this course, sir? So prerequisites for this course are, let me tell you all of you, that the first investment is your time. Let me tell you, the first investment is your time, and the second investment is your dedication, third investment is your sincerity towards the class, and the fourth investment is whatever I say, if I give you any work, that you have to do. And apart from this, what I am saying, you need to have some basics like addition, subtractions, and you must know small trigonometric identities and small differentiations and integration. These are all the investments. क्लास का टाइमिंग क्या है? 7:30 AM. Romish Raja, 7:30 AM. Right? So your time is the investment, and the sincerity is the investment, hard work is the investment, and small basics you need to have. Additions if you know, subtractions if you know, multiplications if you know, differentiation, and small trigonometric identities and differentiation integrations. That to a minimal level only. Right. So digital filter determination using Z transform, and relationship between S plane and Z plane. Right, these are the topics which we are going to cover in Z transform. After that, the next topic is discrete Fourier transform. See, for EE students this topic is not there. For EE students you can skip this topic. Electrical students you need not study, but ECE and instrumentation students you have to study this topic. So frequency domain sampling, what is the concept, analysis and synthesis equations, DFT of basic signals, circular convolution, DFT using linear filtering. In 2021 a problem came from this fifth topic in ECE, and the properties of DFT as usual. So these are the topics which we are going to cover, my dear students. And the books you have to follow. So many times you'll ask the books, no? So these are the books which we are going to, or these are, I don't say that you have to buy and start reading. So first, these are reference books. These are reference books. I think PDFs are available on the net, you can download. So the first and foremost, reference books means anyway we will be discussing each and every topic. But if you want, if you're not satisfied with the topic, or if you want some additional information, you must refer these books. Weightage of SS in GATE for EE, around 8 to 9 marks. Harish Kumar, around 8 to 9 marks you can expect. It varies. I cannot say that 2021 these many marks came, 2022 also those many marks are going to come. I cannot say that, but on an average, generally when something is varying randomly, we'll take the average. So 8 to 9 marks you can take it as average for electrical or ECE. Okay, Harish. So first book is Signals and Systems by Alan V. Oppenheim, Alan S. Wilsky with S. Hamid Nawab. This is a good book. And don't, when I say, Arush, good morning, when I say go through the book, then you start reading. Otherwise you don't go through any book, you will be in trouble. So Signals and Systems by M.J. Roberts, Signals and Systems by Simon Hagen, this is also good book. Linear Systems and Signals by B.P. Lati. And for ECE students, for DSP you can go for John G. Proakis, DSP. And for problem solving, so your next question will be, sir, where can we find more number of problems to be solved? Means, see, you have Signals and Systems, the Sham series, this is one, and RK Kanodia. In these books you will get lot of problems. We'll be discussing many problems in the class. At the same time you can get many problems from these two books. Right. So this is our agenda. You people, if you're having any doubts, so timing, nice timing, sir, 7:30 AM freshly mind. But my dear student Arush, you must come regularly, right? Then only our event will become successful, right? So those who are coming new, please like the session, share the session, and type your attendance by pressing like button. Right. So let's start the show. And again I'm saying, if you don't know any basic, if you don't know anything about signal, if you don't know anything about the topics of signals and systems, don't worry, we are going to discuss everything in detail. Harsha, questions from Fourier series came this year, sir. I felt difficulty in solving. No problem, Harsha. By looking at our lectures, will be confident. If possible, we'll try to take more sessions on the app also, so that you don't have any fear. Most of the students will have fear towards Fourier series, but nothing is there. Harsha, you're from which background? ECE or EE? So let's start. ECE. Okay. ECE means it came. A problem came using the Parseval's relation. So ECE means Parseval's relation. Such kind of problems we are going to solve many problems. Don't think that, sir, in every first class faculty will say that, but you only will see from the following lectures whether you can follow or not, whether we are going to discuss all the concepts or not. Will you conduct separate session for question practice? And see one thing, Guru Balaji, see our intention, our channel intention, Creatrix channel intention is to give you the best in all aspects, but that will happen if you come regularly and more in number. Then you can demand, you need not ask, then you can demand, sir, you conduct separate question practice. Then you can demand, Guru Balaji. If you are coming regularly, then you will have a chance of demanding, right? Definitely will have that session. Okay. EE students also need not worry, you are in safe hands. Right. Fine. I have written something, but here I skipped here. I have written something that what I am expecting from students, from you people. See, as students you will have some expectations from the teacher, right? But as a teacher I'll have some expectations from you people also. But among all the slides I have shown, I think this is the most important slide, because all those slides are available in any textbook you go through or the syllabus. Just I copy pasted the syllabus, but this is important, what I feel. What is that? Regular attendance without fail. Regular attendance without fail. Sir, I am having exams. Sir, I am having I must go outside. You should not come with excuses. Regular attendance must be there without fail. And one more thing is, our subject is an interlinked subject, means if you are not coming regularly, definitely you will have a problem for the next class. So what I suggest is, before coming to the class, go to the previous class notes, because everything is a link. Everything is a link that you only will observe. The third point what I have written is sincere dedication towards homework, because here if I solve it, assume that there are 100 problems, assume 100 problems in signals and systems. If I solve all those 100 problems in the class, it makes no sense, right? So the strategy must be like this. I'll be solving around 50 to 60 problems, and 40 problems you must solve on your own as a part of homework. Then you will get the confidence on the subject, right? Because it is you who are going to write the exam, but it is not me who is going to write the exam, right? So homework, daily homework will be there, sincere dedication towards homework, and interaction in the live classes. So whenever I ask something, because as this is a numerical subject, I'll be asking you some questions, so you must reply, you must be very active in the live chat, right? So that is also I expect from you people, and must have fire towards your goal. Generally what I observed in YouTube is, right, so for the first or second day people will be coming like a flood, but second day slowly people will be dropping. But here what I'm expecting the reverse, right? If 30 people are coming today, means you must propagate, you must share the session so that 60 people come tomorrow. So if you are coming in that way, more initiatives will come for you, my dear students. And hard-working nature, right? You must have hard-working nature, because if you want to be successful in any competitive exam, the sixth one is very much required, hard-working nature, right? Total number of duration complete, So total duration to complete signals and systems, we cannot say Shakti Charan now. As of now I cannot say, because this is online now. Online means we are going to discuss everything in detail. It will take many lectures. I cannot say that in these many hours I am going to complete. Right? So let's start the show. Okay. So our subject is, let me put the heading, signals and systems. Signals and systems. Right. Before going to start the subject, first of all you must know what is the definition of a signal. How we are going to define a signal. I am going to define signal in two ways. First way, signal is a physical quantity. Signal is a physical quantity carrying some amount of information. Carrying some amount of, signal is a physical quantity carrying some amount of information. If anybody asks you the basic definition of a signal, means you must say signal is a physical quantity carrying some amount of information. What is present in a signal? Information is present in a signal. Now then they'll ask, what kind of examples, day-to-day examples you can give for a signal? You must reply like this. Say you are reading a newspaper. In the morning you are reading a newspaper. We have some information about, in the paper we have some information about stock exchange. Stock exchange. Right? As the day is progressing, you might have observed, as the day is progressing, how the market is going to rise and how the market is going to fall. These kind of graphs you might have observed in your paper. It is a signal which carries some amount of information about the stock exchange. Based on this information, so I got information, what you are going to do, I am going to take some decisions whether to buy a share or whether to sell a share. Right? So based on a signal we can take a decision. So other examples what you can give for a signal. Recently elections were held in our country. Elections is a good example. Suppose if a political party wants to analyze how many Lok Sabha seats they have won compared to the previous years. Okay, they want to analyze their performance. So they are going to do like this. Elections came in the year 2004. A particular political party got 65 Lok Sabha seats. Again after 5-year term, elections came in the year 2009. The same political party, they won the majority of the seats. There is a problem with this. They got some 74 Lok Sabha seats. Again after 5-year term, elections came in the year 2013. With overconfidence, what happened? Dropped down to 41. So again elections came in the year, so this is 2014, 2019. So again they performed well and they got some 80 Lok Sabha seats. Right? So this is a signal which carries some amount of information about the performance of a political party. Now by looking at this signal, the political party can take a decision that how we are performing. Right? So we define signal as a physical quantity carrying some amount of information. Other examples also you can give. Suppose nowadays we are stuck up with the pandemic called COVID. Right? Suppose you want to read, this is the month of March, how many cases of COVID were there in your city in the month of February. Suppose if you want to examine, so February 1st, so 1 to 28, so February 1 to 28. So first day only 60 cases were recorded. Okay, second day some 75 cases were recorded. Third day only 40 cases were recorded, so on. So from this what can you do? You can take an analysis, right? So signal is a physical quantity carrying some amount of information, right? So gold prices, if you are going to compare the gold prices of 1 or 2 months, yes, that is a signal which carries some amount of information. You want to know how many babies were born in your city in a 1 month duration. If you are going to record that, that will be a signal which carries some amount of information. So one of your relatives is not feeling well, so we took him to hospital. So the doctor said that go and get the ECG. So ECG is a signal which carries some amount of information about the performance of the heart. Earthquake happened in Indonesia. The team wants to know the intensity of earthquake on a Richter scale. That is a signal which carries some amount of information. So lot of signals daily. Many signals we'll discuss. In our day-to-day life, we are going to have many signals, right? Suppose if you want to calculate your performance, so I'm in the BTech third year, what was my percentage in the first year, second year, third year? Okay, so that will become signal which carries some amount of information. Now I want to check the performance today. How many are watching? 27 watching now. So second day 30 watching, third day 45 watching. So that gives me confidence that students are coming in number. So that is also a signal because information is there. So signal is a physical quantity carrying some amount of information, right? So this is the first definition I am going to give. So after knowing this example, look here. The next thing is how you are going to classify the signals. Sir, would we be providing any questions material for the solving problems, or everything will be provided, Tirtha? But I want my request is that you have to come regularly and more in number, right? So after knowing the definition of a signal, that signal is a physical quantity carrying some amount of information. We'll see how to classify these signals. How you are going to classify these signals we are going to discuss. Right? We are in very basics. We know only definition. Other than definition, we don't know anything about signal. Signal is a physical quantity carrying some amount of information. What is my expectation from the past 5 minutes is that you must know the definition, that information is present in a signal. That's it. After that, signals, remember, are classified. How we are going to classify these signals? Signals are classified or categorized. Signals are classified or categorized based on something known as dimension. How we are going to classify signals? Based on dimension. What is this dimension? Which stands for an independent variable. Independent variable. So after knowing the definition of a signal, that signal is a physical quantity carrying some amount of information, I am saying that these signals are classified based on dimension, which stands for an independent variable. What is this dimension? What is this independent variable? And what is the role of this independent variable in a signal? We are going to discuss now. Now, how we are going to classify? Based on dimension, no? So I am going to classify as something as one-dimensional signals, because these are classified based on dimension. Now I am going to classify them as two-dimensional signals. Fine. I am going to classify them as three-dimensional signals, and I am going to classify them as four-dimensional signals. Yes, you can classify based on dimension. Now let's see example for each case. Coming to the first category called one-dimensional signal. Here the name itself signifies one-dimensional signals. Dimension means independent variable, and remember these one-dimensional signals are those signals which are having only one independent variable. One-dimensional signal means one independent variable, right? One-dimensional signals are those signals which are having only one independent variable. What are the examples you can give for a one-dimensional signal? An audio signal, what we are listening daily, denoted by f of t, can be given as an example of one-dimensional signal. An audio signal can be represented like this. We are going to take a vertical axis and we are going to take a horizontal axis. Along the horizontal axis, one vertical, I think you are comfortable with vertical and horizontal axis. Vertical axis and one horizontal axis. Along the horizontal axis, we are going to represent the independent variable, and along the vertical axis, we are going to represent the dependent variable. Dependent variable means dependent on this one. And remember, Independent variable. Independent variable means it is the quantity of a signal which we can vary. Independent variable means it is the quantity of a signal which we can vary. Here we can give different values of t along horizontal axis and we can record the values along vertical axis. This independent variable and dependent variable, they will have some functional relationship. These two will have some functional relationship, so that as you are going to give different values of t along horizontal axis, you can record the values along vertical axis. So an audio signal, something, it will be shown like this. Audio signal can be taken as example of one-dimensional signal. Suppose if you are from electrical background, a current signal, a voltage signal can be taken as example of one-dimensional signal, because we are having only one independent variable. One independent variable, and this is called dependent variable. Dependent variable, vertical axis always will take dependent variable on the vertical axis and independent variable on the horizontal axis, my dear students. Hope you are comfortable. One dimensional signal means one independent variable. Coming to two-dimensional signals, how many independent variables we can expect? Already we have seen now dimension means independent variable. If one-dimensional signals are having one independent variable, naturally two-dimensional signals will be having two independent variables. Two independent variables. Right? What are the examples you can give for a two-dimensional signal? Right? An image, what we are storing in a mobile or a computer, JPEG image, TIF image, .png. Okay, an image what we are storing in a mobile or computer can be represented or can be taken as an example for two-dimensional signal, where it can be represented like this: f of x comma y. Here only one independent variable, f of t. Here two independent variables, f of x comma y. And remember, my dear students, that this x and y are known as spatial coordinates. Spatial coordinates. So in the first example what I took, independent variable is time here, but in the second image, x and y are spatial coordinates. So independent variable is not fixed. It is not time always. It can be time, it can be space, it can be frequency, it can be anything based on the application. Independent variable depends on the application what you are going to have. So an image is represented like this. A two-dimensional signal, an image. Don't worry, we are going to have a beautiful statement within 5 minutes. An image is represented like this, where we are going to take the spatial coordinate x along horizontal axis and spatial coordinate y along vertical axis. Now you might have observed an image. Image appears like this. Suppose if I say that this point, this intersection point, represents some brightness or contrast. If I call this f as brightness or contrast, it depends on both the independent variable, f of x comma y. Yes, it is for gate only. So f of x comma y. So which gives some information about brightness or contrast. Brightness or contrast. Two independent variables, two-dimensional signal. Coming to three-dimensional signal, how many independent variables we can expect? Naturally, three independent variables. Three independent variables. What are the examples you can give for a three-dimensional signal? A black and white TV picture. Black and white TV picture can be taken as an example of three-dimensional signal. Yes, it is for gate only. Suppose black and white, see, three-dimensional signal with three independent variables. So black and white TV picture. Suppose if I take two-dimensional signal image f of x comma y, see, image is still one. It is not in motion. Image is a still picture. It is not in motion. So brightness or contrast is constant at any point. If brightness or contrast varies with the time, brightness or contrast varies with the time means moving picture. Moving picture can be taken as an example for three-dimensional signal. Moving picture is also a signal, but three-dimensional signal. Now coming to four-dimensional signals, how many independent variables we can expect? Four independent variables. Four independent variables. The best example is the temperature. at a point Acha, I don't write. Okay, so, right. So, okay, Charan, noted. I won't write, sorry. Temperature at a point in a room. Temperature at a point, 4-dimensional signal, temperature at a point in a room. Suppose if I take any point in space, we know that any point in space can be represented with 3 coordinates, x, y, z. And temperature varies from time to time. 4 independent variables, 4-dimensional signal. Now if you observe here, this temperature at a point in a room, this black and white TV picture, or this image, or this audio signal, they all carry some information, right? These all four categories carry some information. So we define signal as a physical quantity carrying some amount of information. Now after this example, what I am going to do is I am going to change my definition of a signal. Sir, how you are going to change the definition? Observe here. My definition becomes like this. Signal is a physical quantity carrying information and can vary with 1, 2 or more independent variables. After looking at those examples, can I modify my signal? In the first case, we have seen that signal is a physical quantity carrying some amount of information, and after that we have seen that signal, can contain 1 independent variable, 2 independent variables, 3 independent variables, or many independent variables. So I modified the definition. Signal is a physical quantity carrying some amount of information and can vary with 1, 2 or more independent variables. So this is the next definition of a signal. So if anybody asks you the definition of a signal, means signal is a physical quantity and can vary with 1, 2 or more independent variables, right? That you must reply. But one good news here is that, one good news is there, that is, as far as any competitive exam is concerned, like GATE, IES or ESE or any public sector undertakings, we are having only 1-dimensional signals in our curriculum. My dear students, we are having only 1-dimensional signals in our curriculum, in which we have only 1 independent variable. Our focus is towards 1-dimensional signals only, in which we have 1 independent variable. We are not having 2-dimensional signals, 3-dimensional signals or multi-dimensional signals in our curriculum. We are having only 1-dimensional signals only. But if you know the concepts of 1-dimensional signals well, you can extend the same to rest of the classifications, because the 2-dimensional signal, 3-dimensional signals will be coming in your engineering as a part of image processing or speech processing, or various subjects are there, no? Right? See, assume that you are going to get a single integral here. Assume that in 1-dimensional signal, definitely you are going to get a single integral. 2-dimensional signal means what will come? Double integral will come. 3-dimensional means triple integral will come. Suppose if I have 1-dimensional Fourier transform, in 1-dimensional signals, if I have 1-dimensional Fourier transform, so in 2-dimensional signal, what you will be having? 2-dimensional Fourier transform. In 3-dimensional signals, what you will be having? 3-dimensional Fourier transform. So knowing the concepts of 1-dimensional signals, is very much essential. Our focus is towards 1-dimensional signals only, in which we have only 1 independent variable and 1 dependent variable, right? Hope you are comfortable with independent and dependent variables. If you are comfortable, I'll go to the next part. Okay, you must be active in the live chat, my dear students. This is the first day. I don't know many of you. Shall I go to the next part? Our focus is towards one-dimensional signals only. Don't worry, everything we are going to discuss in detail. Okay. Right. Electrical students also need not worry. Those who are coming from lateral ending need not worry. Okay. If you are regular, leave rest of the things on me. I'll take care. What I am saying is, if you are regular to the class, leave the rest of the things on me. I'll take care. Right. So definition of a signal, my dear students, my students have understood the definition of a signal. That signal is a physical quantity carrying some amount of information and can vary with one, two or more independent variables. A signal can have any number of independent variables based on the application, but as far as GATE is concerned, only one-dimensional signals, one independent variable and one dependent variable. Right. Now, how we are going to classify these one-dimensional signals? This is an important point, students. Observe here. So these one-dimensional, now from the previous discussion, we came to a point that for our exam, in order to get a single-digit rank or in order to enter any PSU, we are concerned only with one-dimensional signals in which we have only one independent variable. And these one-dimensional signals taking time as independent variable. Now I am classifying into three types. First one is continuous time signals. Second one is discrete time signals. Third one is digital signal, my dear students. Continuous time, discrete time, digital signals. This is the first basic part. Continuous time, discrete time, digital. So first of all, we have seen the definition of a signal and we have seen the classification of signals based on dimension. After that, we came to a point that for any competitive exam, we are having only one-dimensional signals. And we are going to classify these one-dimensional signals taking time as independent variable. Continuous time signals, discrete time signals, digital signals. What are these classification and what are the interrelationship between these classification we are going to discuss now. Observe here. In order to represent the first category called continuous time signals, what I am going to do is I am going to take one vertical axis and one horizontal axis. Right? Along the horizontal axis, we are going to represent, as you know, the independent variable. And along the vertical axis, we are going to represent the dependent variable. Dependent variable means dependent on the independent variable. And this is a continuous time signal. Continuous time signal I have drawn. If this is a continuous time signal, what I have drawn, what is the definition of a continuous time signal? Arey Baba, what is the definition you are going to give? Observe here. The definition you can give like this. Continuous time signals are those signals which are present throughout the continuous time period. Continuous time signals are those signals which are present throughout the continuous time period. Then how you are going to explain? Observe here. The signal is present at 0. Observe here. It has some value, na? The signal is present at 1. It has some value. Signal is present at 2. It has some value. Signal is present at 3. It has some value. Signal is present at 4. It has some value. Fine. Instead, the signal is also present at 0.5. Observe. Signal is present at 0.5. The signal is present at 1.5. The signal is present at 2.5. The signal is present at instant 3.5 also. Instead, the signal is also present at 0.01, 0.01, 1.01, 2.01, 3.01. Or, my dear students, if you can break the interval from 1 to 2 into 1 crore parts, if you can break the interval from 1 to 2 into 1 crore parts, each part will have some value. That is the definition of a continuous time signal. Continuous time signals are those signals which are present throughout the continuous time period. Means you can expect the existence of a continuous time signal at every instant of time. At every instant of time. Whatever may be the instant, 2.1, 2.5, 2.7, at every instant of time, you can expect the existence of a continuous time signal. After knowing the definition, okay, now I am comfortable with the definition of a continuous time signal. Now, after that, you must know what is the nature of this independent variable, independent variable, and what is the nature of this dependent variable. Let me write. The independent variable, what you are going to consider here is time, and the dependent variable forms your amplitude. Again, what is the definition of a continuous time signal? Continuous time signals are those signals which are present throughout the continuous time period. Means the signal is defined at every instant of time on the horizontal axis or on the time axis. Or in short, I can say that the independent variable is continuous. Continuous means it can take any value. My dear students, continuous means it can take any value on the time axis. It can take any value. Any value means continuous. Now coming to the dependent variable, what about amplitude? Amplitude can take any value. Let's observe. See, at 0 you can have an amplitude of 2.5. At 0 you can have an amplitude of 2.5. At 1 you can have an amplitude of 2.5 to any amplitude you can have. Means dependent variable can also take any value. Dependent variable can also take any value, means it is also continuous. Both independent and dependent variable, they can take any values in the case of continuous time signals. So I am saying that they are continuous. They can take any value, means they are continuous, right? So this is the definition of a continuous time signal and the nature of independent and dependent variable. Independent variable can take any value. Dependent variable can also take any value. So they are continuous. Next thing comes, sir, can you give any examples for a continuous time signal? Yes, I can give. Observe here. See, a signal represented of the form xt is equal to e power minus t u of t. E power minus t u of t, which looks like this. Sir, what is this e power minus t? What is this u of t? What is their multiplication? How the signal came like this? Don't worry, we are going to discuss in future how the signal came like this. But for the time being, this signal can be taken as an example of continuous time signal which is defined at every instant of time. This is the example. For the sake of example, you can consider this one. This is a decaying exponential, can be taken as an example of continuous time signal. So from the past 5 minutes discussion, what we have learned, sir? Continuous time signal. Yes, Jayatirtha, you are right. You are right, Jayatirtha. It belongs to a real number, right? So continuous time signals are those signals which are present throughout the continuous time period, and in the case of continuous time signals, both independent and dependent variable, they can take any value, so they are continuous, right? Now coming to the next classification of one-dimensional signal, that is discrete time signals. Now how you are going to define this discrete time signals? But before defining, in order to represent these discrete time signals also, we'll take one vertical axis and one horizontal axis. Here also, in the case of discrete time signals, the independent variable is taken along horizontal axis, but it is denoted with n. Instead of t, we'll denote with n. And the dependent variable is taken along vertical axis, here also defined as f of n. And one more thing is, here in continuous we'll use parenthesis, whereas for representation of a discrete time signal we'll use square brackets here, square brackets. So this is f of t, continuous, parenthesis, like this. Discrete time. This you must observe. Independent variable is t in continuous. Independent variable is n in discrete, right? So this is a discrete time signal. If this is a discrete time signal, what is the definition of discrete time signal you are going to give? Remember, my dear student, that discrete time signals are those signals which are present only at discrete instance of time. Discrete time signals are those signals which are present only at discrete instance of time, not at every instant of time. They are present only at discrete instance of time, or in short we can say like this, or I mean one more definition I can give like this, that discrete time signals are those signals which are present only at integer values of time. Discrete time signals are those signals which are present only at integer values of time. For better understanding, you can observe here the signal is defined at 0, it has some value. The signal is defined at 0, it has some value. The signal is defined at 1, it has some value. Defined at 2, it has some value. Defined at 3, it has some value. But no signal is defined at 0.5 as in the case of continuous time signals. No signal is defined at 1.5 as in the case of continuous time signals. No signal is defined at 2.1 as in the case of continuous time signals. Or we can say that these discrete time signals are absent at fractional values of time, but they are present only at integer values of time. Integer values of time. Now, after knowing the definition, we'll see again what is the nature of this independent variable and what is the nature of this dependent variable in the case of discrete time signals. The independent variable, what we are going to consider is again time, but integer values of time, and the dependent variable forms your amplitude. Dependent variable forms your amplitude. Again, what is the definition of a discrete time signal? Discrete time signals are those signals which are present only at integer values of time, not at every instant of time. If this discrete time signal would have existed at every instant of time as in the case of continuous time signals, we would have said that the independent variable is continuous. But here the signal exists only at integer values of time. So that we are going to say independent variable is not continuous, but it is discrete. It is discrete. Coming to the dependent variable, you only can say dependent variable, it is taking any value, right? So dependent variable is still continuous. Dependent variable is still continuous in the case of discrete time signals, right? Now, after knowing the definition of discrete time signals, the nature of independent dependent variables, the next thing is what are the examples you can give for a discrete time signal. Remember, my dear students, that discrete time signals are represented as sequences. Discrete time signals are represented as sequences. This kind of notation. Our discrete time signals are nothing but set of samples, set of sample values. Set of sample values is nothing but a discrete time sequence. Now, how you are going to represent? So, example I can take like this: 1, 1.5, minus 2, 3, and I'll place a arrow here. This is a representation of a discrete time signal. This arrow indicates the reference point, which indicate the sample value at n is equal to 0. N is equal to 0. To the right side of arrow are n is equal to 1, n is equal to 2 kind of things. To the left side of arrow are n is equal to minus 1, n is equal to minus 2 kind of things. In order to represent this discrete time signal, so take the independent variable. In discrete time signal, independent variable is n. What is the value at 0? 1.5. Give a value of 1.5 in the upward direction. Dependent variable can be continuous. What is the value at 1? It is minus 2. Give a sufficient amplitude of minus 2 in the downward direction. What is the value at 2? It is 3. 3 means give a sufficient amplitude in the upward direction, 3. What is the value at minus 1? It is 1. So this is a representation of a discrete time signal. And remember, arrow indicates the sample value at n is equal to 0, reference point. And in exams, my dear students, if arrow is given, well and good. If arrow is given, fine, we are happy. But sometimes they will skip the arrow. If arrow is not given, by default you must take the arrow at the first point. You must take the arrow at the first point. Suppose this kind of sequence is given to you. 1, 2, 3. This is a discrete time sequence. This is given in exam. Suppose if they give like this, so you may search for arrow. Arrow is not given now. So by default, if arrow is not given, take the arrow at the first point, right? If it is not given. So if it is given, well and good. We will proceed with the given arrow only, right? Now, this is what is your discrete time signal. Now the next question what arises is, after knowing the definition of continuous time signals which exist at every instant of time and discrete time signals which exist only at integer values of time, is there any functional relationship that exists between continuous time signals and discrete time signals? Is there any relation? Yes, there is a relation. By a process known as sampling, continuous time signals are converted into discrete time signals. Or sampling is the relationship that exists between continuous time signals and discrete time signals. Anyway, we are having separate unit on sampling, separate unit dedicated around 7 to 8 hours discussion is there on sampling. But in a nutshell, how we are going to have this sampling? Observe here. The sampling operation, look here, the sampling operation, which is nothing but the relationship between the continuous time signals, and discrete time signals, is nothing but a switch operation, my dear students. Remember, sampling operation is nothing but a switch operation, where the nature of the switch, what we are going to take is, the switch will be closed only at particular instance of time, not at every instant of time. This switch what I am going to take here will close only at particular instance of time given by t is equal to nts. At the input of the switch, I am going to give the continuous time signal x of t, and at the output of the switch, I am going to collect the discrete time signal denoted by x of nts. And always remember, sampling operation for the time being only. For sampling operation means independent variable t in a continuous time signal simply replace with nts. Sampling operation means independent variable t in a continuous time signal simply replace with nts, where this ts is known as sampling period. Ts is known as sampling period or sampling interval, which is nothing but distance between adjacent samples in a discrete time signal. This is your sampling period. This is ts. So sampling means independent variable t in a continuous time signal simply replace with nts, where ts is known as sampling period. For example, what we are going to do is, discrete EG signals question every year in GATE, sir. Every year discrete time signals will come Jaya Tirtha. You must have more concentration towards discrete time signals. Every year in GATE, see, there is no partiality. Continuous time signals will come, discrete more, you must emphasize more on discrete time signals also for GATE, right? So for example, here what I am going to do is, I am going to take a continuous time signal like this, which is e power minus t u of t, which we have drawn here, decaying exponential continuous time signal defined at every instant of time. Now I am going to feed this to a sampler, and what I said, sampling means independent variable t replaced with nts. In continuous, wherever you have t, replace with what? Wherever you have t, replace with nts. So what is the physical significance of replacing this t with nts? How we are going to multiply with impulse train, Nyquist state, Nyquist interval calculations, that anyway we are going to discuss. But for the time being, replace t with nts, so that x of nts is equal to e power minus nts u of nts. Means now we are going to draw against nts. We are going to draw x of nts against nts. Now here always remember, whenever you are going to replace your t with nts, this n must be an integer always. This n must be an integer value only. This ts may be an integer, may not be an integer. It may be a real number ts, but n must be integer. N must be integer always, right? So here 0, first substitute n is equal to 1 ts, 2 ts, 3 ts. So if you collect the sample at 0, here I am going to get one sample, at ts, at 2 ts, at 3 ts. I am not going to take all the information, but I am going to take the information from certain samples only. Now what after this, what we are going to do is, we are going to normalize the time axis. Actually the process is, we are going to normalize the time axis. Normalization means dividing with something. We are going to normalize the time axis with the ts. What happens if I divide each and every point with the ts? So this by ts if I divide, this by ts if I divide, this by ts if I divide, 0, 1, 2, 3, so on will come, no? So in this way we are going to have a discrete time signal from a continuous time signal by a process known as sampling. Now you can observe the switch is closed at 0. We got a sample between 0 to 1, that is after normalization this became 1 now. So between 0 to 1 the switch is open, so we didn't get any sample. The switch is closed at 1, we got a sample. Between 0 to 1 the switch is open, so I didn't get any sample. The switch is closed at 2 and the process is repeated. So for the time being, you remember that sampling operation means independent variable t replaced with NTS. Independent variable t replaced with NTS. TS is known as sampling period. Right? Okay. Are you comfortable, my dear students? So after normalization, what will happen? Our signal will look like this, something like this. Hope you are all comfortable. Discrete time signals, they exist only at integer values of time. Continuous time signal, they exist at every instant of time. Right? Now after this, look here. So we came up to discrete time signal. We started our journey with continuous time signals and we came up to discrete time signals. Now after coming to discrete time signals, what is the nature of the independent dependent variables here in discrete? Independent variable is discretized. Independent variable is discretized with sampling. Independent variable is discretized with sampling, but dependent variable is still continuous. And we know that if we want to process any signal on a computer, computer understands only in the language of ones and zeros. Now our aim is to convert, observe here my dear students, our aim is to convert these continuous amplitudes. Our aim is to convert, now my aim is to convert these continuous amplitudes in discrete case to discrete amplitudes. Continuous amplitudes in discrete case to discrete amplitudes, which is done by a process known as quantization. Quantization. So by a process known as quantization, discrete time signals are converted into digital signals. Quantization means for the time being round off. Suppose if you are having a value of 2.5, you can round it to 2 or you can round it to 3 so that you can give the binary representation. Binary representation you can give. Right? Now you tell me, can you tell me what is the nature of independent dependent variable in the case of digital signals? What is the nature of independent dependent variables? Can you type your answer in the chat box? What is the nature of independent dependent variables in the case of digital signals? Come on. Both are discrete. Both are discrete. Both are discrete. Or we can say that these digital signals are nothing but discrete time signals only. Digital signals are nothing but discrete time signals only, but with amplitude quantized. Digital signals are nothing but discrete time signals only, but with amplitude quantized. Right? And there is one more process. Basically, after quantization, there is one more process called encoding, with which we are going to get a clear digital signal. So this much knowledge is enough for you. As far as signals is concerned, this much knowledge is enough for you. Now if I ask you one question, that yes, exactly, you are all right. If I ask you one question, that if I want to discretize the dependent variable, to which operation I must go? If I want to discretize the dependent variable, I must go for quantization. If I want to discretize the independent variable, go for sampling. If you want to discretize, yes, see, discretize independent variable, sampling, discretize dependent variable, quantization. Let me write that. Discretize independent variable. Discretize independent variable. Sampling. Sampling is very interesting, one of my favorite topics. Discretize dependent variable. Go for quantization. Go for quantization, right? So this is the classification. Hope you are all comfortable, my dear students, right? So first of all, we started our discussion with the definition of a signal. That signal is a physical quantity carrying some amount of information and can have one or more independent variables, and we are concerned with only one independent variable. So continuous time, discrete time, digital. Continuous time is they exist at every instant of time. Discrete time signal means they exist only at integer values of time. Relationship is sampling. Sampling means t replaced with NTS. Okay, and by a process known as quantization, discrete time signals can be converted into digital signals, right? And we are looking at some examples, right? How to how to sample independent variable t replaced with NTS. So that is done with the help of a switch. So wherever you have t replace t with NTS and normalize with TS. Normalize means divide, and this x of NTS automatically becomes x of n. This x of NTS will automatically, representation is x of n. More number of examples anyway we are going to discuss, right? The next topic what we are going to discuss is an important topic, my dear students. Important topic. Now what is the independent variable? Next question is also like this. What is the independent variable in the case of continuous time signals? Time. And what is the independent variable in the case of discrete time signals? It is also time, but integer values of time. So independent variable plays a major role in the case of one-dimensional signals. So the next topic what I am going to discuss is the transformations of the independent variable. Let me tell you, if you are going to miss this topic, you will face lot of problems in the subject. Transformations of the independent variable. Very interesting topic, you will enjoy like anything. Transformations of the independent variable. Independent variable we have seen. Now what transformation you can perform on the independent variable we are going to discuss. How many hours did you take class, sir? Sir, there is no limitation for hours. So it's like until you get perfection. Until you get perfection, that many hours. That is only the answer. So transformations of the independent variable. Basically, what are different types of samples? What are different types? I didn't get you, Lokesh. What are different types of samples means what? Samples can be integer values or they can be anything. Okay, there are three transformations of the independent variable. What are different types of sampling or samples? I didn't get you. So there are three types of today I'll take for 5 more minutes and leave you, as this is a first class. I don't want to trouble you much. So there are three transformations of the independent variable. First one is time shifting. Time shifting operation. Independent variable is time followed by the operation you can shift. Samplings. Lokesh, we have different types of samplings, like impulse train sampling is the basic sampling, and apart from that we have practical approaches like natural sampling, flat top sampling. If you are from electrical background you don't have this, but natural sampling, flat top sampling will come for EC students in communication also. And we have something known as band pass sampling in time domain. If you are going for frequency domain, again we have frequency domain sampling. Don't worry, Lokesh. So we are in very basics. We are small babies today. They are just born now. Don't think much in the first class, right? Just follow my words for 15 days and see your progress. Time shifting, time reversal, time scaling, time shift. These are the three transformations of the independent variable we are going to have. So I'll do one thing, as the time is 8:45. I'll do one thing. I'll close my session as this is the first day. So I don't want to take for longer time. So this what is this time shifting, what is this time reversal, what is this time scaling. For continuous signals we have to discuss, discrete time signals we have to discuss, and what happens, we are going to combine all the operations and what are the available methods and shortcuts we have, we must discuss in detail. So at least I think tomorrow we will have a whole topic on transformations of the independent variable only. But for tomorrow's class, prerequisite is go through today's class notes. That is, you must know what is continuous time signal, discrete time signal definition and their relations. You must have for tomorrow's class, and if you are comfortable, then you can master this independent variable. And our aim for tomorrow's class is, given any transformation of the independent variable, we must be in a position to solve. You must challenge your friends that are give any transformations of the independent variable, I can get the answer for you. So that is the idea for tomorrow's class, and I am expecting you people to be in large number, right, my dear students. And tomorrow I'll take till 9 o'clock, 9 a.m. So don't forget this. Regular attendance without fail. Before coming to class, go through the previous class notes. Sincere dedication towards homework. Today first day, no homework. Interaction in the live class. Must have fight towards goal. Hardworking nature, right? And after that, you can follow me on Unacademy, my dear students. Unacademy.com at KV Swamy, and I have done some couple of videos on the app also, special as a part of special classes. You can go through the classes and you can see how we are going to deal each and every topic. You can just go through the app and observe. Right, you can follow me on Unacademy, and various advanced topics, some topics I took, and I'm going to discuss some advanced topics also. You can observe, and these are the channels what we are having in Unacademy. So this is our channel, Creatrix, GATE ESE